Okay, so welcome back to this next video in which we're discussing the effect of sympathetic stimulation on the heart. Okay, so we are trying to understand how releasing noradrenaline onto the cardiomyocytes results in increased force of contraction in those cardiomyocytes. Okay, so far we've decided that in order to get increased contraction, what we need is a higher amplitude of calcium spikes in these cardiomyocytes so that we can recruit more sarcomeres to contract and therefore get a greater force of contraction. We have now seen how you can increase the amplitude of those calcium spikes, i.e. by phosphorylating the L-type voltage-gated calcium channels and by phosphorylating the type 2 ranitidine receptors, which is going to result in larger calcium spikes in the cytoplasm of the cardiomyocyte and therefore greater recruitment of sarcomeres in the cardiomyocyte and therefore greater force of contraction. However, this would be pointless if you did not increase also the activity of the SERCA2 pump, which is pumping calcium back into the sarcoplasmic reticulum, because you need these still to remain as calcium spikes, i.e. you need the calcium to go back to this extremely low level. The reason being, if you don't get it back to the low level, then the sarcomeres will not have time to recoil back to their original position, i.e. some of the sarcomeres will remain contracted basically, and then when you come to the next action potential, what will happen is you will already have sarcomeres mid-contraction basically, which means that you can't get the same level of work out of them because if they're already contracted, they can't contract anymore basically. So you need complete removal of the calcium so that all the sarcomeres relax back down to their original length, and then when the next calcium spike comes, you can contract them all again. That's the way to get the maximum amount of work you can. So we're now going to discuss how does beta-adrenergic stimulation activate the SERCA2 pump. So this time it's through type 1 protein kinase A. Okay, so we've discussed how noradrenaline combines to, in fact we'll draw this here. If we have the plasma membrane here, we've discussed how noradrenaline combines the beta-1 adrenergic receptor, which is this G protein coupled receptor with 7 transmembrane domains here. So we draw this in vivid purple here. So this is the beta-1 adrenergic receptor. Okay, so noradrenaline will bind to that, or norepinephrine, or whatever you want to call it. So here it comes and binds to this beta-1 adrenergic receptor. That will then activate the heterotrimeric GS G protein. So here is the heterotrimeric GS G protein with the alpha S subunit here, which we'll colour in blue. Okay, so this is the alpha S subunit. When that alpha S subunit is turned on, i.e. by having GTP bound to it rather than GDP, it will then go and activate the adenylyl cyclase 5 or adenylyl cyclase 6 enzyme, shown here. Okay, with these 2 transmembrane regions. Right, so this is either adenylyl cyclase 5 or it's adenylyl cyclase 6. Okay, and we'll show the adenylyl cyclase enzyme in red here. Okay, and this adenylyl cyclase enzyme will now convert ATP into cyclic AMP and pyrophosphate. Okay, so this is producing cyclic AMP, which we'll show as a little orange ball. And this is now going to act on the type 1 protein kinase A, which is free within the cytoplasm of the cardiomyocyte. So we'll show the type 1 protein kinase A here. So here are these regulatory subunits, which are of the first type. So these are R1 regulatory subunits. Okay, so here are their cyclic AMP binding sites here. Okay, and they have these 2 catalytic subunits bound to them, which are inactive in this state when they're bound like this. So this is the R2C2 complex of a type 1 protein kinase A, so protein kinase A, and then we'll put Roman numeral type 1 afterwards. Okay, so let me colour this in. So we'll have the R1 regulatory subunit in this bright fluorescent green colour here. Okay, so this is in fluorescent green. And then we'll have the catalytic subunit in, what colour should we have it in? Pink, I think. Okay, so here in pink is the catalytic subunit of the R2C2 complex. Well, two catalytic subunits. Now what's going to happen is that the cyclic AMP that you've produced from the adenylyl cyclase 5 or the adenylyl cyclase 6 is going to bind to our type 1 protein kinase A. It's going to cause the regulatory subunits to change conformation. So these are the R1 regulatory subunits because we're talking about this free or soluble or type 1 protein kinase A, whatever you want to call it. So it's got these R1 subunits. And the cyclic AMP is going to come and bind to these 4 cyclic AMP binding sites, like so. And when that cyclic AMP binds, it's going to change the conformation of the R1 regulatory subunits so that they now release the catalytic subunits. So these R1 subunits are still in this bright green colour here. Okay, like so. Oops. Okay, and when they change conformation like that, they're going to release these catalytic subunits. So off come the catalytic subunits here of the protein kinase A enzyme. So these are the catalytic subunits. And these are now going to go and phosphorylate certain proteins. Now, in this case, what they're going to go and phosphorylate is a protein which is associated with the SERCA2 pump. So here are our catalytic subunits. So now let's discuss our SERCA2 pump. So if this is the membrane of the sarcoplasmic reticulum here, then basically here is the SERCA2 pump, which, remember, pumps 2 calcium ions into the sarcoplasmic reticulum lumen in exchange for free protons moving out of the sarcoplasmic reticulum lumen. So here come the free protons. And every time it does that, what it will have to do is hydrolyze adenosine triphosphate, ATP, into adenosine diphosphate and an inorganic phosphate molecule. Okay, so I will colour this in orange. Okay, and this is the SERCA pump, the sarco/endoplasmic reticulum calcium ATPase. And it's specifically SERCA of the second type that you find in cardiomyocytes. Right, okay, now, normally in a resting heart, in a heart that is not in a fight or flight situation and is therefore not receiving beta-1 stimulation, there is another protein here called phospholamban. So this is phospholamban. Okay, phospholamban. And phospholamban, which is often also called PLB for short, phospholamban. Phospholamban basically associates with SERCA2, binds to SERCA2, and inhibits it. Okay, stops it from functioning to its full ability, basically, reduces the amount of calcium it is returning into the ER. Now you can guess what's going to happen. The catalytic subunits of the type 1 protein kinase A, they're going to come over to phospholamban and they're going to stick phosphate groups onto it. Okay, like so. So here's a phosphate group now bound to this phospholamban. And when the phospholamban has phosphate groups bound to it, it no longer functions. So it drops off the SERCA2 pump, stops inhibiting it, and that increases the activity of the SERCA2 pump. So you've now increased the activity of the SERCA2 pump, and that means that in this phase of the cardiac contraction where calcium release has now stopped, i.e. when you're up here, calcium release has now stopped because the calcium has inhibited the type 2 ranitidine receptors. The action potential has passed. The L-type voltage-gated calcium channels are no longer letting calcium in. Both of those things contribute to the termination of the release of calcium, And now the Circa pump is going to take over. It's going to return the calcium back into the SR. That's going to lead to the reduction of the calcium level, and we've just activated the Circa so that it works quicker, and it's going to need to because we released more calcium, so it's got more work to do, and it needs to do it in the same amount of time, basically. And because we have now stopped the inhibition of Circa2 by phospholamban, it can now do that. It can work quicker, and you'll get this quicker, you'll get this reduction in the calcium concentration happening in the same amount of time, even though the amount of calcium it needs to return into the SR is greater. So indeed, we've got what we wanted, basically. We've got calcium spikes that are of a greater amplitude, but are still returning the calcium concentration back to this 100 nanomolar, practically zero level, in between consecutive calcium spikes to allow for the proper relaxation of the sarcomeres. So that's excellent. Okay, now we'll continue our discussion in the next video.